Good morning. I want to talk to you a little bit today about something called the Hertzsprung-Russell diagram, often referred to as the HR diagram. And this is probably the most important chart or diagram in all of astronomy because what it does, it was developed about 200 years ago by two guys aptly named Hertzsprung and Russell, and it's used to classify stars by their temperature and their luminosity. And luminosity again means brightness. So here's a look at the HR diagram. It is sometimes referred to as the periodic table of astronomy, which if you remember from chemistry, the periodic table is the most important chart in all of chemistry. So the HR diagram is a very valuable tool used by astronomers. And what it does is it plots on the y-axis here luminosity or brightness. Now our sun is denoted as a 1. So our sun is the starting point. So as we move up, you can see it's a logarithmic scale. So we're moving up, 10 to the second, 10 to the fourth, 10 to the sixth, and luminosity or brightness. If we look down here, the only, I guess, tricky part of this HR diagram is that the temperature moves from right to left, and it gets higher as we go up. So if you take a look at the very bottom, we have the temperature starting out at 40,000 Kelvin, and it decreases as we move from left to right, which is a little counterintuitive to what we're used to. But what happens is we can take a look at a supergiant, a red supergiant, and we can see that it is extremely bright, but it has a very low temperature. And because it's so massive, even though it's not all that hot compared to other stars, it indeed is very bright. We take a look down at our white dwarfs down here. Now, white dwarfs are not going to be very luminous, but they're extremely hot. They're very hot, but they're dim. We take a look in the middle here, we see that the majority of the stars, as you already know, are main sequence stars, and our sun is right in there as well. So these are main sequence stars, and they're stars that are still burning, still using hydrogen to fuse to helium. If we take a look at a blue giant star, now blue is the hottest color star. Blue are very, very hot stars, and they're also very luminous. So if you take a look at the chart here, they're hot and they're luminous. So they're hot and bright. The HR diagram, what it can do is it tells you quite a bit about a star. Again, if we start with our sun as a basis of 1, luminosity of 1, then we can get an idea of how bright and how dim other stars are. If we take a look again down here in the corner, we have some cool dim stars down here. They're not very luminous and they're not very bright. And they have a low temperature. So the HR diagram plots star brightness versus its temperature. And it gives us an idea of what stage or what evolutionary part of the cycle a star is in. Now, I did mention color just before, and the temperature of a star can often be determined by its color. We often think of hot as red color, but in this case, stars that are blue are the hottest stars, then white, and then yellow, and then orange, and then red. Now, it says here our sun is a yellow star, but our sun is actually more of a whitish color star. But that's okay. These colors are just denoting the various temperatures. So if you see a star as Antares, you know that it's a red giant, but it's also going to be a bit of a cooler star. Surface temperature is quite less than that of our sun. Here again is just a quick way of looking at colors. This is all in Kelvin here. So blue are the hottest, blue to white are the second hottest, and then white stars, and we go down, and the red stars are the coolest stars and temperature wise. Now they're all still really hot, but compared to each other, blue is the hottest star, red is the cooler, lower temperature star. We take a look at the constellation Orion, as we have done many times. Betelgeuse right here is a red giant. So actually a red super